this is in this lecture, what we do, we present examples of common circuits and blocks that people see in digital designs that need to be implemented in Verilog. Um, Obviously, we cannot give all the examples that people can think of, but we kind of give snippets of examples of circuits that we already studied, and we see how they can be translated into Verilog code. One thing important about this language, Verilog, that there is always more than one way to implement a design or to implement a circuit. So when we present an example, that does not exclude all other implementations. This is just to show you how you can express and implement the circuit in Verilog. And by all means, there are other ways of doing it. Okay. Now, let's take, for example, here implementation of a multiplexer. Mhm. So let's see if I get this one here. Okay, so you can see here a multiplexer here. It is a 4-to-1 multiplexer. So I am kind of checking these select lines, right? And the way we're implementing this is that we are doing it two levels. This is the very first level, right? Whoops, sorry. That's fine. And then I have a second level of the multiplexer. Okay, and then after the first level, we move to the second level, all right, of the multiplexer. Okay, and in the first level, well, that didn't come up the right way. Um, okay, but anyways, in the first level of the multiplexer, the select signal is S1, okay, and in the second level of the multiplexer, which is this one here, okay, okay, so I have S0, okay. Something is funny here in my drawing this morning, so let's just to clean this up. Okay, and let's try to do it the right way. So basically, you have here the let's traverse the language. Sorry, let's traverse with the language. Okay, so we have two select signals here. Okay, so and I have four inputs, A, B, C, D. I'm going to use the first select signal here between choosing between C and A, and or D and B, and then I will record the output in a temporary variable. Then I will use the second select signal, which is bit 0, to choose between T0 and T1. So this is two-level multiplexer. Okay, but at the end, I'm going to choose one of those, A or B or C or D, okay, and send it to the output. Now, we know that we have covered this design before, but what we want to highlight is the use of parameter here for width. So what's the use of parameter here? Well, suppose, for example, I need to have a multiplexer, a 4-to-1 multiplexer for any number of bits, for 2-bit, for 4-bit. So the data width can vary. Now I can use parameters here, right? That I can have it as almost like a variable that can be set in the implementation. Okay, so let's see if I can clean this mess here. Okay, so notice that here the parameter. Okay, let's see if I get this one here. Notice that here the width is a parameter. I'm giving it a default value of a 1. Now I'm saying that my A, B, C, D, these are inputs. These are of width of the parameter width, which can be any number. One, it has to be integer, by the way, positive integer. And here I can have the output is defined the same way, right? And the intermediate variables and the output are defined with this way as well. Now, in the instantiation, I can instantiate this multiplexer and say max 4. Okay, we use this sign here, and I'm passing 32. This 32 goes all the way to the width. This is as if I have replaced the width with the number 32. So the MUX4 magically becomes now a 32-bit 4-to-1 multiplexer. Okay, so this way we can parameterize our design. I don't need to implement a 2-bit 4-to-1 multiplexer and a 4-bit 4-to-1 multiplexer and an 8-bit 4-to-1 multiplexer and a 16-bit 4-to-1 multiplexer, etc., etc. I just implement one 4-to-1 multiplexer with a parameter width, and this width can be set during the instantiation. I can instantiate this mux again, another mux with parameter of 8-bit. Okay, so during the instantiation, these parameters they are very, very, very useful in Verilog if you are creating a parameterized module. I use them quite a bit in my coding. Now, here is another way of using a parameter here. We are doing a comparator here, all right? And the word size, what we are comparing. So we are comparing A and B, right? But their width is a parameter. So A, B can be set during instantiation as 2 bits or 4 bits or 8 bits or 16 bits or 32 bits or 64 bits, etc. To be able to do that, I make the word size as a parameter which can be set during the instantiation. Okay, all right. Now, this is how, excuse me. This is how I implement a tri-state. A tri-state output, it means that there will be an enable here. If this enable is set, then I will have a 1 or 0 on the output. But if the enable is disabled, then I will have high impedance, which means Z value. So how to implement high impedance? It's very simple. So you compute this multiplexer here, you do all your work here. Then the output of this multiplexer here comes in here. Okay, so comes in here, and then we say that the multiplexer output, which is this one here, right? Which is this one. Oh, if I could just move my mouse. Okay, which is this one here. Okay, it is equal to, if the enable is 1, then it is equal max int, which is what is coming out of the multiplexer. If the enable is disabled, then I'm gonna set this output here to high impedance, and the output happens to be 32-bit. So 32-bit tick BZ, it means 32-bit of Z values. Okay, so this is how I set the tri-state. So I use an assign statement here. Okay. Now, here's an example of doing encoders. Okay. So the encoder is a combinational circuit where we have a 2 to the n input, and the output is n, right? And the input will be of this shape 00001 or 00010. And so in this case, we have an 8 to 3 encoder. Okay, so we will encode these values. The implementation, one possible implementation, is using the f else, f else, f else, f else. A parallel implementation of that will be the case statement. I prefer the case statement. Both are okay, but really when the if statement has f else, f else, f else, and then I don't like using the if statement. I like to use the case statement. So we case the data here. Okay, and whenever the value equal to this, then the output, which is the code, is this. So when the data equals 000000001, then the code, which is the output, equals 0. If the data is equal 10000000, then the output code is 7. Okay, so the case statement and this if statement do exactly the very same thing. Okay. Now, we can have a priority encoder in which you can have things like, For example, what happens if you have like 1 1 1 1 1 1 1, all are ones? Because in the classic encoder, only one of the inputs can be active. We call it one hot. But when you have multiple of these bits that can be set, like for example, 1 1 1 1 1 1 1, so what should be the output? In this case, we use a priority encoder, which means that we give the priority for the higher bit. Again, you can use F statement, or you can use a case. All right. So the case statement says that, by the way, both are the same. In this case statement says case this data, right? And if the upper bit is 1, I don't care about the rest of the bits, then the code is 7. Now, if the upper bit is 0 and the bit 6 is 1 and the rest of the bit I don't care about them, then this code is 0. So you're giving priority basically for the higher bits, right? And this is exactly also what's being done in this if statement. When you say if data 7, you are basically ignoring the rest of the bits, okay? So this is the implementation of priority encoder. Again, this is an encoder which encodes in the case of more than one of the bits are being set. Now let's take a look about decoder design. Decoder design. So for you have an input, right, and you want to decode it, right? So you can have implementation with case, and you can have implementation with if else statement. I like the case. Okay, and both do the same thing. So if you have your code here, if your code is 0 and the decoder, and you want to decode it, so your output, so this is by the way a 3 to 8 decoder, so the output will be 0 0 0 0 1. If your input for as a code is 1, so the output will be 0 0 0 0 1 0. Okay, observe that the decoder does exactly what the encoder does. Okay, so they do the opposite thing. Okay, the same thing is implemented here in the case in the if statement. If the code is 0 equal to 0, then your output is 0 0 0 1. If the code is 1, 0. If the code is 7, then your output is 1 0 0 0 0 0 0. So this is implementation with if else. This implementation with the case statement. They both do the same thing, but I prefer whenever you have a lot of branches for the case statement, especially for data selection or data checking, I prefer using the case statement. Also, I prefer to use it in implementing finite state machine. Okay, I don't like using the if statement, and have seen people also prefer that most of the times. Okay, so if statements are used for simple conditions, if else. You don't want to really have this really lengthy number of branches. Okay, so here is an example of 7-segment display, and how would you display it? So basically, here you have an input which is a BCD, right? It has the value that need to be displayed, and the output which is a display. Now we're using parameters here to set the output bits, and these are kind of our constants here, or parameters. Okay, so in the code, I check the value of my input BCD, and I set the display to the correct values. By the way, this is meant to be for clarity. I can get rid of all of this and just set display right away to the value of the 0. Okay, but this is meant for readability, and this is a good example how parameters can be very helpful and useful for readability. Okay, so again, in this example, what we are doing, we receive a BCD input to be displayed on 7 segments. So I check the BCD with a case statement, the value of it, and I set the display to the appropriate output value. Here are flops as we have taken them in the previous section. There is nothing I add here, but just more examples. Okay, so here is a classic flip-flop without any reset, classic flip-flop with an enable. Okay, the thing to highlight here, watch the sequential circuit how implemented, always with non-blocking assignment. Okay, and the at pause edge of the clock here for the flip flop. Okay, so this is something to watch. Of course, the Q here is always of type register. Okay, so the Q should be of type register. I'm not sure why we are not. It should be register. The Q type should be register. This should have said Q output register. Okay. Okay, more flop examples. Okay, this is with a reset. In this case, we are using synchronous reset, and this is asynchronous. The difference is the asynchronous, we check on the sensitivity list the value of the reset. Okay, now here is okay, the difference between synchronous and asynchronous. Okay, D flip flop. Um, Nothing to be add from what I have explained, more examples. So you can, I'm just looking for, the latch is, does not have this at pause edge of the clock. It just checks the let's say if we just check the value of the enable. Okay. So we can, for example, if I remove this pause edge here, this becomes a latch. Okay. By the way, people used to be crazy about design of based on latches, but nowadays they are all registers because they are easier to be checked by many of the CAD tools. Latches are headache. Okay, so what else here we have? Registers. Okay, if we have multiple flip-flops, then the name changes from a flip-flop to a register. That's the convention. Okay, it's the same design here, but just multiple bits, right? Okay. Now, the one thing Verilogs offers you, if you implement in hardware a lot of instances, so they allow you this generate here. I have used it in the past. Um, Kind of nice, but you really had to have to be accurate. I would consider these constructs to be useful for those with some kind of experience with Verilog. For beginners, I would not advise using them because really sometimes they exhibit certain funny behaviors, and you have really to it throws you into these really cycles of debug. So, but anyway, they kind of suppose I want to repeat this statement, right, to instantiate many of these flip-flops. So to save me typing here, right, I can use this generate statement, which will generate this statement for how many this loop will go. Okay, so it kind of saves space in typing Verilog. Okay, all right, and it creates for you funny names here, for instance names. And as I said, I would not advise you. It's very helpful, but I wouldn't advise it for to be used by a beginner in Verilog. They have their own issues, that subtle issues that really they throw you into sometimes a debugging sessions, and if you are a beginner, try not to use them unless you have really some experience with Verilog. Okay. Okay, so here is a register where we can load data to this register. Okay. Okay. So if load equals 1, then data gets data in. Okay, this is the parallel load. Okay. All right. Um, okay. And what happened if I don't have load? Well, basically keep the old value of the data. So you kind of load this register if load signal equals 1, and what's the data is going to come from data n. Otherwise, if not load is not present, what do? We don't do anything. Well, and for some, this is similar to an enable, a flip-flop with an enable. Okay, I think we gave this example here. Probably we showed a flip-flop with an enable. Yeah, this is it here. It's like a flip-flop with an enable, but instead of just one bit of data and one bit of flip-flop, we have many bits in this example, and that what makes it a register. Okay, all right. So we have 1, 2, 3, 4 bits. In the previous example with the enable swap was 1 bit. So this looks like an enable, this load here. Here's a shift register, and what we are doing, we are shifting the data like so. Okay, so if there is a reset, I will have all the register values will be zeros. Otherwise, I will shift the data, which means that the value of the register will take the input value and the 3 bits, because we are shifting this data. Dn will get in here. Okay, this q will get in here. This q will get in here, and this q will get in here, and the data out leaves. And I'm sorry, this queue will they will leave to data out. Okay, so you can see that this data out equals. So I think the enumeration is this bit 0, bit 1, bit 2, and bit 3. Okay. Here is a barrel shifter. Okay, and basically we are doing a rotation of the data like so. Okay, so this is to the, let's see, to the left. Okay, so the data out, we will get these bits plus. Okay, so you can see here. Okay, you can see here how this data is shifted. Okay, we're going to shift this bit to here, and this bit to here, and this bit to here. Okay, etc. And this bit to here, and this bit will rotate all the way and come in here. And that is the meaning of this statement. Okay, so d out equals 60. Okay, plus the 7-bit goes to the least significant bit. Okay, right. So this is the original, and this is the output. Okay. All right, and we have this universal shift register, which does a shift, I think, in both directions. I'll leave this example for you to look at and debug. Very simple, kind of use shifting and parallel load and etc. So check it out yourself. If we have more than one register, so one flip-flop, we call it 1 bit is one flip-flop. If we have a 32-bit flip-flops, we call it a register. If you have multiple registers, right, then we call this entire thing a register file. Okay, so you can see how we define register file. This register file, each register is a 32-bit. I'm sorry, each register is a 32-bit. And how many registers we have? We have 32-bit registers. So this is the width of the registers. This is the number of registers. Okay, and we can access these registers by what? By an address. Okay, so notice here what we are doing. We are assigning the value of this register, which we have received the address as an input, right? As an input here. Okay, and we assign it to this. We kind of here perform we perform a register read. What happens if we want to perform a register write? It will be used in this always block. We have a value to write, and this is the register, and this is the register number. Okay, register file, register number. So the data will go to this register number at the pause edge of the clock. So we are reading data asynchronously, and we are writing to the register synchronously. Okay, so that's so in this you can see that probably should have looked at this block diagram. So these are the two read registers. This is the write address. This is the data which is used to write. And these are the two data that we read out from the register file. And the write enable is used to do the writing for the register. Okay. This is an example of up-down counter. Okay. Which again uses let's see, a control signal that will tell me should I count up count or down count. Okay, so um, also this register allows me to pre this design allows me to pre the count with an initial value. So suppose, for example, I want to start counting from, let's say, from 0011. Okay. Um, so I can preload the counter. Okay. And if activate this load signal to be 1 and give it the start counting value at data end. Okay, if load is not equal to 1, then we will check if the counter is on. If the counter is on, we'll check the count, is it up or down? Okay, so here is the counter. We have the start counting value, right? Which is enabled by this load signal, and this is the count, the counter on that tells me that if I can count now or I cannot, and this is the signal that tells me to can count up or down. This is the output of the counter. Okay. This is a ring counter. I will let you take a look at it yourself. It's just shifting one through this ring register. Very simple example. With that, we conclude these examples of Verilog code that are commonly used in digital systems, and this concludes the Verilog lectures. Thank you very much.